In this video, we will finish Chapter 6. We're going to cover Section 6.6 using the normal distribution as an approximation to the binomial distribution. And here, what we're doing is we're using our normal distribution to approximate the binomial probability distribution, right? We're starting with a discrete random variable and transitioning it to a continuous one. And that will come with its own challenges of changing the type of random variable. So in a binomial distribution, we're given a probability of a success P and a probability of a failure Q. And what we want to do is to translate that to a normal distribution, right? Normal distributions need a mean and a standard deviation, and we use the exact same formulas we had for mean and standard deviation of the binomial distribution, where mu is n times p and sigma is the square root of npq. This will transition us to a normal distribution with mean mu and standard deviation sigma. We said that there would be challenges when transitioning from a discrete random variable to a continuous random variable, right? And the difference is the discrete has defined outputs like x is equal to 1, 2, or 3. And in a continuous random variable, we get things like x is less than 3. And what we need to do is we need to correct for this change from a discrete to continuous. And what we do is we get what's called a continuity correction, where we take a whole number in the discrete random variable x and transition it to the interval of x minus 0.5 to x plus 0.5 to be able to fill in those continuous gaps. So for example, if a discrete random variable has an output of 3, the continuity correction would give us a range of 2.5 to 3.5, right? Minus a half and plus a half from those values. And we'll see how this works in practice later on. Okay, let's briefly review the binomial probability distribution. We've stated that a distribution has a binomial distribution if it has a fixed number of trials, we call it n. Each trial is independent. Each trial can be classified as a success or a failure, and the probability that each trial is successful is constant. And we said that that probability was lowercase p, right? And here are really the main notations that we've used. That n was our fixed number of trials, x was the specified number of successes, p is the probability of success, and q would be the probability of failure, which we represent by 1 minus p. Okay, let's talk about why we want to use the normal distribution as an approximation. Here we're going to look at Mendel's famous hybridization experiments, where he tests whether certain traits were dominant or recessive. And here he's looking at the number of yellow pea pods that will come out of offspring when the choices fall between yellow and green. And we can see what he's doing is he's looking at doing 580 trials with the probability that each trial will come out yellow to be 0.25. What he saw when he did this experiment was he saw 152 yellow peas, and he wanted to know whether this was significant or not. And as we've seen with the normal or with the binomial distribution, that if we wanted to compute something, the probability of getting at least as many trials, we would have to add all of those cases together, which would be adding all the numbers from 152 to 580, which is a lot of trials. So how can we get around this? And if we look at the outcome chart listed below, we can see that this thing looks very normal distribution-like. So what we'll do is we can just pretend that this is a normal distribution and compute a mean and standard deviation and use what we defined as that continuity correction to have a good approximation for what this solution will turn out to be. For us to have a normal approximation, we're going to need a mean and a standard deviation. The mean is going to be NP. So mu is going to be N, the number of trials, times the probability that any trial is successful. And if we compute that, we'll get 145. Our standard deviation is going to be the square root of NPQ, which is 580 times 0.25 times 0.75. And if I compute that in a calculator, we'll get 10.43. We will use these values in our normal approximation to compute the probability of events motivated by this example. The other very important thing when using the normal distribution as this approximation is to correct for the fact that we're moving to a continuous random variable. And so we need to adjust the discrete whole number x by using an interval from x minus 1/2 to x plus 1/2. So for example, in our discrete example, our x was 152. When we transition to the continuous, we're going to represent that not by 152, but by a range of 151.5 and 152.5. Sorry, 152.5. Right? We'll actually get a range. And we'll have one of two values to pick from when we do our z-score calculation. We'll talk about how we figure out which of these 2 points later on. Okay, so how do we actually do this? How do we use the normal distribution to approximate the binomial distribution? There are technical requirements. We're not going to worry about this. All of the examples we have will follow that. So our first actual step is finding the mean and the standard deviation we need to use for our normal approximation. Next, we need to identify the discrete number x that is relevant to the binomial problem and find its continuity correction, the interval that it represents, where x is minus 1/2 and x plus 1/2. What we're going to do is graph our normal distribution and shade the region or the area that is bounded by one of these two as appropriate. Okay, so let's do an example of this. In Mendel's experiments, he expected that among the 580 offspring peas, 145 of them, or 25%, would be yellow. But when he did this experiment, he got 152 yellow peas. So what we want to do is compute the probability of getting more than 152 yellow peas. That is, given 580 trials and a probability of a successful trial being 0.25, I want to find the probability of at least 552, or I'm sorry, the probability of at least 152 yellow peas. What we're trying to compute is this a significantly high value? Is his theory wrong? Or does it fall within a certain appropriate margin of error? Okay, so for us to do this, we're going to need to come up with our mu, which is NP, which we computed already. That's 580 times 0.25, and we got 145. We're also going to need to compute our standard deviation, again, which is the square root of NPQ, which is the square root of 580 times 0.25 times 0.75, which again we computed as 10.43. Right? What we're going to do is we're going to draw a normal distribution with our mean of 145. And our x value, right, in this problem was 152, which we said we want to change to the interval 151.5 and 152.5, right? This is our continuity correction. So that's what we're going to do. Here's 151.5, here's 152.5. And it could be that interval. And now we have to remember what we're computing. We want the probability of at least 152 yellow. So at least means the probability that x is greater than 152, right? At least means greater than or equal to. And so if I look at this, I want to shade the region all the way to the right of 152. But if I think about my two continuity correction points of 151.5 and 152.5, if I use this as my data point and shade the area to the right of 151.5, that shading will actually include the point of 5152. Right? So when I translate this to my normal, I want the probability that x is greater than 151.5. And so now I turn a binomial problem into a normal distribution problem. And we can solve any normal distribution problem. Okay, if I want to compute the probability that a normal random variable is greater than 151.5, remember, we have to convert this to a standard normal curve. And to do that, we need the z-score of x minus mu over sigma. But we have all these with our normal approximation to the binomial. Our data point here is 151.5, our mean is at 145, and the standard deviation is 10.43, what we computed in the previous step. If we compute these calculations, we'll get 0.62. And again, because we're computing the z-score, this needs to be 2 decimal places. So when I translate to the normal, standard normal distribution, I want the probability that a standard normal random variable is greater than 0.62. And how do we do this? I'll draw my standard normal curve. 0.62 is going to be here. I want the probability of being larger than that. This is the area to the right. Remember, our table gives us area to the left. So to compute the probability that z is greater than 0.62, I need to compute 1 minus the probability that z is less than 0.62, and that will give us our table value. So let's look at our table. Okay, here we have our positive z-score part of the table, and I want the probability that z is less than 0.62. It has an area to the left of 0.62, so I have 0.6 and my 0.02, and that is my probability. The probability that z is less than 0.62 was 0.7324. So we can bring that over to our problem and finish our solution. Okay, so we found our probability. That's 1 minus 0.7324. And as a final answer, we'll get 2676. That is the probability of getting at least 152 yellow pea pods. So the final question in this example was, is this significantly high? And so we computed the probability of getting 152 or more yellow peas was 0.2676. If you use other computer-generated methods, like this PowerPoint did, you get slightly different probabilities, but our probability is still good enough. And we see that that is not a really high probability, right? So that result could easily occur within our actual true rate. The experiment does not contradict Mendel's theory, that it still holds true. That's how we would use the continuity correction to use the normal distribution to approximate a very difficult binomially distributed problem. I do want to talk a little bit more about the continuity correction itself. And when we use the normal distribution to approximate the binomial distribution, that continuity correction is made because we're taking a discrete whole number and changing it to an interval. Right? We're going from a discrete number to a continuous number, and we need to fill in the gaps in between those discrete numbers. And when we solve problems using the normal distribution, we often see language of at least, at most, less than, and greater than. And so what we want to do is we want to see, well, if we have 2 points that we use in our continuity correction of 151.5 and 152.5, a common question is, well, where do we want to use 151.5 and where do we want to use 152.5, right? Which point do we want to use? And it all depends on the language. It all depends on how we shade the region, right? If I want at least 152, that means I want 152 and above. I want to include that value. So I want everything to the right of 151. If I want more than 152, I only want to be larger than. I don't want to include it. So the point I use out of 151.5 and 152.5 has to be the value that when I shade in the region does not include 152, and that's 152.5, right? That is slightly bigger, and so when I shade the area into the right, that will not include the actual value of 152. And we can see the other examples kind of flip, that if I want at most 152 successes, that is 152 or smaller. That is an area to the left. And the data point that includes the value of 152 with an area to the left is going to be actually the 152.5. And if I want fewer than, that does not include 152. So I want to use the data point here that does not count 152 to the left, and that would be 152.5. Something we almost never answer in a continuous case is the probability of getting exactly. If that was the case, I would want the probability of falling in between those two things. That would be the probability that 151.5 is less than x is less than 152.5. And we would have to do 2 z-score conversions to find the standard normal distribution for those 2 values. Okay, let's compute that. Let's find the probability of getting exactly 152 yellow peas, right? This is the binomial probability. I want to convert this to the normal probability. So I need my mean, again, which is NP, which we've computed in this example before. It's 145. And I need my standard deviation, again, which is square root of NPQ, which we've computed before. That's 10.43. And again, that value of x equals 152 is going to convert to the interval of 151.5 to 152.5. So if I draw my normal curve, here's 145, 151.5, 152.5, and the probability of getting exactly 152 will correspond to the probability of 151.5 being less than x being less than 152.5, right? That's the probability of falling in between these two values, which we can use the z-score to convert, right? The z-score to convert to standard normal. But we'll need 2 z-score calculations. So let's do that. So again, when we compute the probability of falling in between, I'm going to need 2 different z-score calculations. For 151.5, right? If I use the values we've had before, rounding to 2 decimal places, I'm going to get 0.62. And if I compute the z-score for 152.5, we will get, with 2 decimal places, 0.72. So our new probability is the probability of falling in between 0.62, and 0.72, right? That is on a standard normal curve, 0.62, 0.72, the probability of falling in between. And we've talked about that before. If I want the probability of lying in between two values on a standard normal curve, well, all I have to do is compute the probability that z is less than our right value minus the probability that z is less than our initial value. So let's read these values off on the chart and finish this example. So let's use this positive z-score part of the table to compute our final answer. And we're lucky that we're looking for two z-scores that are really close together. I want 0.62 and z being less than 0.72, and they're going to be right on top of each other. Here's 0.62 and 0.72. So let's bring these values over and finish our example. So we can finish this example using the probabilities we found on our chart. So we get 0.7642 minus 0.7324. And if we compute that, we'll get 0.0318. And that will be our probability of getting exactly 152 yellow pea pods. I hope this was helpful. If you want to see other examples, feel free to email me and we can set up a Zoom office hours. If not, good luck, and I will talk to you next time.